For most of human history, nobody actually knew the Milky Way wasn't the entire universe. The faint, hazy band of light stretching across a dark night sky was assumed to be everything, the full extent of all the stars and matter that existed anywhere. Even into the early 20th century, plenty of professional astronomers still believed that certain fuzzy, spiral-shaped smudges visible through telescopes, what they called spiral nebulae, were simply clouds of gas drifting somewhere within our own galaxy. Nothing more exotic than that. It took one astronomer, one very specific type of star, and one very careful measurement to prove that assumption catastrophically wrong, and everything NASA has found beyond the Milky Way in the century since traces directly back to that single moment. The astronomer was Edwin Hubble, and in 1923, working at the Mount Wilson Observatory in California, he identified a particular kind of pulsating star, called a Cepheid variable, inside one of those fuzzy spiral smudges, a formation known as the Andromeda Nebula. Cepheid variables are useful to astronomers because they brighten and dim on a predictable schedule directly tied to their true luminosity, which means measuring how that brightness cycles lets you calculate exactly how far away the star actually is. When Hubble ran the math on the Cepheid he'd found inside Andromeda, the distance that came back was staggering, far too great for the star to possibly sit anywhere inside the Milky Way. Andromeda wasn't a nearby gas cloud at all. It was an entire separate galaxy, sitting roughly 2.5 million light-years away. And if Andromeda was its own galaxy, then so, almost certainly, were countless other spiral smudges astronomers had been casually cataloging for decades without understanding what they were actually looking at. In a single measurement, Hubble had proven the universe was vastly, almost incomprehensibly larger than anyone had previously imagined. That discovery eventually earned Hubble something more permanent than a place in astronomy textbooks. When NASA and the European Space Agency built and launched a space telescope in 1990, specifically designed to study the universe from above the distortion and light pollution of Earth's own atmosphere, they named it after him. The Hubble Space Telescope inherited a mission built directly on its namesake's original discovery. Keep looking outward, past our own galaxy, and figure out exactly what's out there. It got off to a rocky start. Shortly after launch, engineers discovered Hubble's primary mirror had been ground with a flaw so subtle it wasn't caught during manufacturing, but severe enough to blur every image the telescope produced. NASA sent astronauts up on a servicing mission in 1993 to install corrective optics, essentially fitting the telescope with a pair of glasses. And once that fix was in place, Hubble began producing some of the most transformative images in the history of astronomy. None of those images mattered more than what became known as the Hubble Deep Field. In late 1995, astronomers pointed Hubble at an apparently empty, unremarkable patch of sky in the constellation Ursa Major, roughly the size of a grain of sand held at arm's length, and left the telescope staring at the single tiny spot for 10 consecutive days, collecting light continuously. Conventional wisdom at the time suggested that patch of sky, chosen specifically because it appeared to contain nothing of interest, would turn up little more than a scattering of faint stars. Instead, when the image finally came together, it revealed roughly 3,000 galaxies packed into that single postage stamp-sized region of sky. Galaxies of every conceivable shape, size, and age, some of them among the most distant objects ever observed at that point in history. It was one of those rare scientific moments that instantly reshapes how an entire field understands its subject. If a seemingly empty patch of sky held thousands of previously invisible galaxies, then the universe as a whole had to be almost unfathomably more crowded with galaxies than anyone had dared to estimate. Hubble repeated and refined that experiment over the following years, staring even longer and even deeper into other patches of sky to produce the Hubble Ultra Deep Field and later the Extreme Deep Field, pushing the total observed galaxy count in these tiny slices of sky up toward 10,000. Extrapolating that kind of galaxy density out across the entire observable sky, astronomers eventually arrived at an estimate that's become one of the most frequently cited numbers in modern cosmology. More than 1 trillion galaxies exist within the observable universe, each one containing, on average, hundreds of billions of individual stars. It's a number so large it borders on meaningless to actually picture, but it traces its origin directly back to Hubble's decision to point a telescope at what looked like nothing and stare at it for over a week. Hubble's contributions to understanding the universe beyond our own galaxy went well past simply counting how many others existed. By carefully measuring how the light from distant galaxies gets stretched toward longer, redder wavelengths as those galaxies move away from us, a phenomenon called redshift, astronomers using Hubble data helped confirm and refine measurements of exactly how fast the universe is expanding. In the late 1990s, observations of distant exploding stars called Type Ia supernovae, many studied using Hubble, led to one of the most genuinely shocking discoveries in the telescope's history. The universe's expansion isn't slowing down over time the way gravity alone would predict. It's actually accelerating, being pushed apart faster and faster by a mysterious, still poorly understood force that scientists now call dark energy. That single realization, built substantially on Hubble Space Telescope data, ended up reshaping essentially the entire modern understanding of how the universe is structured and where it's ultimately headed, and it earned the astronomers behind it the Nobel Prize in Physics in 2011. Hubble also spent decades documenting the sheer variety and violence of what exists beyond the Milky Way's borders. It photographed galaxies caught in the middle of colliding and merging with each other, their spiral arms stretched and warped by gravitational tidal forces into long, glowing streams of stars. It captured supermassive black holes at the centers of distant galaxies, actively feeding on surrounding gas and dust, and used the motion of stars near the Milky Way's own galactic center to help confirm that a supermassive black hole sits at the heart of our galaxy too, a finding later built upon by ground-based observatories that eventually captured actual images of black hole shadows. And through a phenomenon called gravitational lensing, where the immense gravity of a foreground galaxy cluster bends and magnifies the light from galaxies sitting far behind it, Hubble was able to peer even farther back in cosmic time than its own optics alone would normally allow, using massive galaxy clusters as natural cosmic scale magnifying glasses. For more than 3 decades, Hubble carried essentially the entire weight of humanity's deep space observational capability on its own. That changed on December 25, 2021, when NASA, along with the European Space Agency and the Canadian Space Agency, launched the James Webb Space Telescope, a successor built specifically to see even farther, and even earlier, into the universe's history than Hubble ever could. The key difference comes down to wavelength. As light from extremely distant galaxies travels toward us, across billions of years, the ongoing expansion of the universe stretches that light toward longer, redder wavelengths, eventually shifting it out of the visible spectrum entirely and into the infrared. Hubble could see some infrared light, but Webb was purpose-built around it, equipped with a much larger primary mirror, over 21 feet across compared to Hubble's roughly 8 feet, and instruments specifically tuned to detect exactly the kind of deeply redshifted infrared light that the earliest galaxies in the universe emit. The payoff came almost immediately. In 2023, Webb revisited the exact same patch of sky that had produced the original Hubble Ultra Deep Field decades earlier, and where Hubble had needed over 11 days of continuous observation to capture that region's faintest galaxies, Webb matched that same depth of detail in roughly 1/10 the observing time, while also revealing previously invisible young galaxies that Hubble's instruments simply couldn't detect at all. Where Hubble had shown astronomers that the point of light from a distant galaxy existed, Webb's superior infrared sensitivity let scientists start actually studying the hot, ionized gas glowing within those same galaxies, effectively mapping out exactly where new stars were actively being born inside them, a level of detail Hubble's original deep field images could never have provided. Then, in 2024, an international team working with Webb's data announced something that immediately became one of the most significant extragalactic discoveries in the telescope's short history. Astronomers with the JWST Advanced Deep Extragalactic Survey, known as JADES, confirmed the existence of 2 extraordinarily distant galaxies, formerly designated JADES GS Z14-0 and JADES GS Z14-1, dating back to just 300 million years after the Big Bang itself, making them the earliest and most distant galaxies ever confirmed at that point. What made the discovery even more remarkable wasn't simply the distance involved. The more distant of the 2 galaxies, JADES GS Z14-0, turned out to be measured at over 1,600 light-years across, and startlingly bright for something that ancient. Many of the universe's most luminous objects generate their brightness from gas spiraling into a supermassive black hole producing what's known as a quasar, but the research team determined that this particular galaxy's light was instead being produced by genuine, actively forming young stars, evidence that galaxies were assembling large populations of stars far earlier in cosmic history than most existing models had predicted, a finding astronomers on the Discovery team described as completely unanticipated. That same year, Webb turned up something else nobody had directly witnessed before. An active merger between 2 galaxies and between the supermassive black holes sitting at each of their centers, captured at a moment when the universe itself was only about 740 million years old. It marked the most distant black hole merger ever detected, and the earliest confirmation that this specific kind of galactic collision, 2 galaxies and their central black holes gradually spiraling together and eventually combining into one, was already actively happening when the universe was still in its relative infancy. Findings like that feed directly into one of the biggest open questions in modern astrophysics: exactly how the enormous supermassive black holes found at the centers of most large galaxies today, including our own, managed to grow so massive in a universe that's only been around for roughly 13.8 billion years in total. Webb hasn't limited its attention purely to the most distant, earliest galaxies either. It's spent considerable time studying galaxies that are cosmically speaking right next door, and turning up genuine surprises there too. In 2024, astronomers using Webb detected the first substantial population of brown dwarf candidates ever, confirmed outside the Milky Way, found within a star cluster called NGC 602, located in the Small Magellanic Cloud, one of our galaxy's small satellite companions. Brown dwarfs occupy a strange middle ground in astronomy, too massive to really be called planets, but not quite massive enough to sustain the nuclear fusion that powers a true star. And finding a substantial group of them in another galaxy, for the first time, gave researchers a completely new environment in which to study how these in-between objects actually form. Even more strikingly, Webb has turned up direct evidence of complex organic chemistry, the kind of molecules scientists associate with the basic building blocks of life, sitting in galaxies well beyond our own. In research published in 2025, a team led by NASA and University of Maryland scientist Marta Sawilo used Webb's infrared instruments to detect large organic molecules frozen in ice surrounding a young, still-forming star called ST6, located inside the Large Magellanic Cloud, another of the Milky Way's satellite galaxies. Among the 5 carbon-based compounds identified were methanol and ethanol, both types of alcohol, along with methyl formate, acetaldehyde, and, notably, acetic acid, the primary component of vinegar, marking the first time acetic acid had ever been detected anywhere outside the Milky Way. What made the discovery particularly significant wasn't merely finding these molecules existed at all, but that they formed under harsh, metal-poor conditions inside that galaxy, conditions that closely resemble the kind of environment believed to have existed throughout much of the early universe, suggesting the fundamental chemical ingredients associated with life might have been available in far more places and far earlier in cosmic history than scientists had previously assumed. Separate research, also using Webb, dug even deeper into that same general theme by examining an ultraluminous infrared galaxy cloaked in thick surrounding clouds of gas and dust. Peering through that obscuring material using infrared light, researchers detected an unexpectedly rich collection of carbon-based compounds hidden at the galaxy's core, including benzene, methane, and even the highly reactive methyl radical, a molecule that had never previously been detected anywhere outside the Milky Way. The galaxy, once dismissed as an unremarkable dust-choked object, turned out to be functioning almost like a hidden cosmic chemical factory, quietly assembling complex carbon-based molecules deep inside a shroud of dust that had kept its true chemical complexity hidden from every previous generation of telescopes. Webb has also continued the long tradition Hubble established of revisiting classic patches of sky and finding dramatically more inside them with newer, more sensitive instruments. In observations released in 2025, Webb pointed its mid-infrared instrument at the same general Hubble Ultra Deep Field region for nearly 100 continuous hours, the telescope's longest single-filter observation of any extragalactic field attempted up to that point, producing one of the deepest views of the universe ever captured. That extended observation alone revealed more than 2,500 individual sources packed into a comparatively tiny patch of sky, including numerous small, greenish-white galaxies whose light had been shifted so dramatically toward infrared wavelengths that their high redshift, and therefore their extreme distance and age, was immediately apparent just from their color in the resulting image. Taken together, everything NASA has learned from beyond the boundaries of the Milky Way traces an almost continuous line stretching back exactly 100 years. From Edwin Hubble's original 1923 realization that Andromeda was its own separate galaxy entirely, through the space telescope that carries his name, proving the observable universe holds over 1 trillion galaxies and is expanding at an ever-accelerating rate, driven by a mysterious dark energy nobody fully understands. And now into the era of the James Webb Space Telescope, confirming galaxies that were already forming stars just 300 million years after the Big Bang, watching supermassive black holes merge together when the universe was less than 1 billion years old, and detecting the actual chemical ingredients associated with life itself frozen in the ice of neighboring galaxies. Each new instrument hasn't just added incremental detail to what came before it. It's repeatedly revealed that whatever astronomers thought represented the edge of the known universe was never really the edge at all, just the limit of what the previous generation of technology happened to be able to see.